Welcome back everyone. So, we are studying NPTEL course on topological phases of matter. Today will be the last part of this chapter, which is topological superconductivity, and this is also the last part of the model Hamiltonian before we start symmetry, and then we will come back to some of the symmetry related topological insulators. And today we will start superconductivity. So, topological superconductivity, before I introduce, I want to tell you a bit about the mean field Hamiltonian of superconductivity, not an exhaustive introduction to superconductivity, but the relevant part of the Hamiltonian way and how to construct the Hamiltonian of superconductivity. And then we will talk about this famous model for a topological superconductivity called key-type p-wave superconductivity. And for this, I think the reference will be Michael Tinkham book, and for this one I think key-type model, Alexei key-type, and I think it's PRB, probably 2008 or so. Okay. With the Google search you will find it, it is a very famous paper. Mean field Hamiltonian of superconductivity. So, superconductivity is a state of the matter or phase of many body electrons. So, that means there is a phase transition, and at that phase transition the resistivity goes to 0, and also something called a Meissner effect, in which the magnetic field is 0 inside the material. Okay. So, it is a complete diamagnetism. And this happens below some temperature called superconducting transition temperature or Tc. Okay. This is the phenomenology, and the mechanism, which is called the BCS theory, 1957, in which they showed that electrons, all the electrons having the same charge, they are supposed to repel electromagnetically, but with a mechanism for an effective attraction between them due to electron phonon coupling, electron forms pair. Form bound pairs called Cooper pair, and when they form a pair, they go to a new ground state which is lower than the normal metallic ground state. Okay. And the reason for that is electron phonon coupling. And later on something called unconventional superconductivity. Which started with the discovery of copper oxide superconductor. Called cuprates in 1987, and later on many families were discovered in which the electron phonon coupling is not the mechanism of superconductivity, but rather there is a leading, it's still a unsolved problem, but there is a leading evidence that spin fluctuation mechanism which means it is actually the repulsive interactions among electrons with a many body effect between them and screening of the electron's charge as seen by an electron with opposite spin or even same spin with a different momentum state, which are connected by some spin fluctuation wave vector, sees an effective attractions between them at those q values. It is not a global attractive interaction for all electrons with any momentum, but only those electrons which are connected through each other through a spin fluctuation or magnon or magnetic fluctuations see an effective attraction between them, or staying at different momentum at different lattice sites, they effectively form some sort of a bound state. Okay. And what that requires is a momentum dependent superconducting pair. Okay. And one more thing I forgot about to say about both conventional and unconventional superconductivity is that there is an energy gap that develops between the superconducting ground state and the excited state or the metallic state, and that gap is called delta. So, for conventional pairing this delta will be momentum independent, and for unconventional this will be k dependent. Okay. So, now we are not going to talk about the mechanism and the entire theory of superconductivity, but rather we will start with a generic Hamiltonian, many body Hamiltonian, which can be derived from an electron, starting from an electron phonon coupling and using second order perturbation theory or more sophisticated theory to get into a two electron interacting Hamiltonian, and or starting from a Coulomb interactions like a Hubbard interaction and long range Coulomb interaction and a density interaction more generically, you can get to a Hamiltonian which will look like this. So, V k and k prime is the effective electron-electron interaction, and we are assuming that this interaction is attractive for one of these mechanism, and in general also we are assuming that this is k dependent. For electron phonon coupling case it will be more of a k independent, but for a spin fluctuation case it will be k dependent. So, I am starting with something general. I am also putting spin indices which are for electron we will choose it to be up and down spin, and we start with whatever the interactions, mainly the density interaction of any sort, and which in the second condensed form can be written with this, an electron being created in the momentum state k and a spin sigma, and here in general it will be k prime or even k plus q, but we know that eventually we are looking for a superconductivity with k and minus k, and right now I am keeping the spin to be general. So, it can be up and down spin Cooper pair or an up and up spin Cooper pair. So, I am keeping it to be sigma prime, and then from momentum conservation and spin conservation and hermeticity condition you will see that the other two terms will be this. Okay. With reordering of this creation and annihilation operator you can get to most of this generic Hamiltonian you obtain either from electron phonon coupling or spin fluctuation mediated or so on and so forth. Okay. And from there we define a mean field gap called order parameter, and I am assuming this to be to have the energy dimensions, because I will include the V into it, this potential. So, it will become a energy dimension. So, this will also give you the energy gap function. Okay. And let me use a different color to highlight it. So, it will be delta sigma k So, it is a convention that we put a negative sign there, suggesting that it is an attractive interaction with V being positive. Okay. It is just a convention to use, does not do anything else. This is a number, and then the expectation value of this quantity. Okay. I change the k to k prime to define something as a energy gap for a given spin at a given wave vector k, which will be summed over k prime and then this guy. Okay. So, again it can be k and k prime, and I am assuming to be symmetric, or is just a change of notation, dummy variable. Okay. So, here we are taking an expectation value. We assume that there is an expectation value of this quantity that is finite for a new ground state. So, this is some superconducting ground state. Okay. on it. So, now one thing that comes for superconductivity, so superconducting order parameter which do not appear for charge density wave for magnetic case is the fact that this is still two electrons coming together in a given state, if you like, and two electron sort of forming a Cooper pair. If you exchange them, there is, because they are fermion, there is a exchange phase of pi, which means it has to be, the wave function of a Cooper pair has to be antisymmetric, or you should get a -1 if you exchange the two electrons within a Cooper pair. So, you have, at least the way I have written, I have not put any orbital indices for this discussion. I do not need the orbital index, but in principle you can also have the orbital index, but without the orbital we still have two quantum number here. One is k, so I can exchange, I can have the spin to be same and there are different k values. So, once I exchange the electron, the k value has to change. And the second one is I can have the spin to be different, and then if you exchange the two electron, you should get a, or I can have both of them, then also you have to worry about. So, eventually if you exchange either spin or momentum or both, one is supposed to get a negative sign. So, the total wave function has to be negative. So, you will have singlet pairing, which is C k up, C minus k down minus C minus k down, C k up. Or we wrote it like this, right? And you can put a half just for convention. So, there we are not changing the momentum, but we are changing the spin and we get a negative sign as we do it for singlet. And also one more thing we do is that we often take a so what about the momentum part then? The momentum part then has to be symmetric, right. So, how do we look at the momentum part? So, it is V k and k prime. So, we interchange them, then this one has to be symmetric. So, this is antisymmetric, this is symmetric. So, let me put it, spin part is -1 antisymmetric, and momentum part is, so total is -1. Okay. So, spin singlet is even in momentum, called even parity. Okay. And generally, if you can have S wave, so that means there is no momentum dependent, it is a local pair. You can have D wave, in which you will have k is equal to plus k, and D wave means it is the same orbital symmetry as the d orbital, whereas the wave function has those discrete symmetry. So, angular momentum being L equal to 0, L equal to 1. Okay. So, this is one possibility. The second one is triplet. So, you have the same spin pairing, both of them has total spin to be plus 1 or minus 1. There is also one more combination, which is, let me write them as up up, down down, and we know that there is supposed to be one more two or square root, depends on how you normalize it. I will use the standard one. This one generally is very hard to obtain, so we will stick to this. So, now spin part is symmetric. If you exchange this two electron with same spin, you do not gain any phase. So, spin part is plus 1. So, the orbit the momentum part then must be minus 1. So, which means you need to have a pairing symmetry that changes sign like this. And okay, there are other ways to represent this in spherical harmonics and so on and so forth. So, I am not going into those details, and what that would give is delta k equal to minus delta, as you change k to minus k as you require to do, as the two electrons have the opposite momentum. So, you are required to change k to minus k, and these are called odd parity, odd in momentum. So, odd parity. Okay. And the examples will be p wave pairing. So, the angular momentum L equal to 1, and then I must have said this to be wrong. This should be L equal to 2. Okay. You can also have F wave, which are again very difficult to obtain. So, this is the second one. These are spin triplet, odd parity, spin triplet. A p wave looks like this: some constant times sin kx for px sin ky for py orbital for px plus minus py orbitals. And these things are near the high symmetry point, they act as linear and now this should remind us, these are the terms that we have been looking for to get topological phases in the off diagonal term especially. We try to obtain those with graphene band structure, with Rasper spin orbit coupling, with hopping between even and odd parity orbitals, and now we obtain the fourth possibility, which is through P wave. So, these things should then give us some sort of a topological phase. Okay. Before we do that, let us write the Hamiltonian. So, mean field Hamiltonian called Bogoliubov-de Gennes Hamiltonian. So, let me BDG which is nothing but the BCS mean field Hamiltonian. So, I only talked about an interacting part. There is also a non-interacting part of the Hamiltonian, which is kind of how a tight binding Hamiltonian, and we will have some dispersion, and we are not putting a spin dependent one. Unless you have spin orbit coupling, these things are spin independent, plus Hermitian conjugate, and the interacting part with the substitution of mean value in this part. So, taking a mean value, so this becomes a number. So, left with this term as an operator, and you will also have the delta star or delta Hermitian conjugate, that is nothing but the expectation value of this, and then you will be left with this term as the operator. So, this is kind of a pairing between two electrons, this is a pairing between two holes, and they have to come together. So, you do have a particle hole symmetry, which we will learn separately in the next chapter. Okay. And there is some ground state energy which works as delta square or delta k prime divided by v k prime. Let me ground state energy, which is like delta k prime divided by v k prime k prime sigma prime. Okay. So, we do not need to be very careful about this term, because this is kind of a overall energy shift, and if these are the ground state energies, so what these guys are? So, these guys are nothing but the excitations from the ground state. So, these are now a quasi particle, not the same electrons anymore. I mean, although we are writing it in terms of the electrons, but these are kind of a electrons that is coming out from the ground state, BCS ground state, which is kind of a condensation of all the Cooper pairs. So, it is a lot of electron that goes there forming Cooper pair, and there is no limit of how many electrons can go. So, that is why it is a condensate. It is a different type of condensate called BCS condensate, and these are the excitations. So, these excitations, whether they form a topological phase or not, is what we are going to study, and that is called the topological superconductivity. So, let me just set it off the Hamiltonian. Okay. It is better to do it in a separate lecture. So, we will do that in the next lecture. We will set it up the mean field Hamiltonian in the usual 2 by 2 form that you are used to seeing it, so that we can connect into that Hamiltonian back to the SSH like Hamiltonian that we have looked into, so that we can figure out the topology very easily. So, with that, let me stop here and see you in the next class. Thank you very much for your attention.